and check that it is actually recording. Yep, it is. All right, so I'll just go ahead and bring up all the files that I was working on before. Okay, so one is LibreOffice cisp310 and ods.ex.ods. And then the other one is just a text file. All right, so this is nothing more than just a base conversion. And then the other one is the text file that I was working on, which is more important than this. So we'll have a mouse pad, cisp310 ex.txt. All right, so this is where we left off last time. I figure out the bit pattern. Are there any questions about how I figure out the bit pattern? Because that really is the most important part. Is, you know, okay, I look at the number, it's represented by an integer times a power of 2. Now that power of 2 can be a positive power of 2, can be negative power of 2. Okay? But what I want to do is to move the point, okay, to the place that it needs to go. So instead of using 101, which is 5, I want to shift it eventually to become 1.01. But every time I change the binary point position, I have to adjust the other value to make up for the shifting of the binary point. Let me just point out where I'm talking about here. We started off with the value that we want to represent, okay? One particular integer times a power of 2. Then I represent the integer in binary. I represent the power of 2 also in binary. And then I shift the point in the integer part until the mantissa becomes 1 point something something. And the rest I can compensate by adjusting the exponent, or the power of 2 that I'm multiplying. Are there any questions about how I ended up with 1.01 times 0.0001 in binary? So this is not in decimal, everything is in binary on that side. Any questions about this part? Okay, if there are no questions about that part, then we end up with a conclusion of, oh, okay, we want a mantissa to be 1.01 in base 2. Obviously, the -4 is in base 10. Yep, go ahead.
And the mantissa stands for exactly what?
The mantissa stands for the multiplier to a power of something. So when you use scientific notation on a calculator, okay, the number before the e something, that's called the mantissa.
Okay.
And most of the time, you want to normalize the mantissa, like what we just do here. So instead, in base 10, for instance, instead of specifying 123.45 times 10 to the power of -6, okay, you usually want to normalize, and so it becomes 1.23 blah 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 times 10 to the power of, in this case, -8, because I have to compensate for the shifting of the point. Is that making any sense? All right. Okay, so that's what I have done so far, okay? So, but I don't want to know the entire mantissa because this part is always implied. It's always there. It is not represented as a part of the 64-bit number. So I get rid of that part, which is left with only the fraction part. The fraction part is basically everything to the right-hand side of the binary point, which starts with a 0, 1, and then the rest are all zeros. So that's why the fraction is 0, 1, and then followed by a whole bunch of zeros. The fraction part is 52, let me see, yeah, 52-bit wide, okay, because the most significant bit is the sign bit, followed by 11 exponent bits. The offset exponent is 1019, because this number is 1023 plus the actual exponent that we want. The actual exponent in base 2 that we want is -4. So when we add -4 to 1023, which is the bias that we need to apply to the exponent component of a floating point number, the end result is 1019, which is a base 10 number. 1019 as a base 10 number, using the spreadsheet, I converted that to 0, 111, 11111, no, 0, and then 111, 1111, okay, and then 011. Okay, I use a spreadsheet to do that conversion. The other thing you can do to check whether this exponent is actually correct is to do the calculation backwards. Okay, you can basically say, is this number 2048 minus 1024 minus the other missing one, which is a, what is that? This is a 1, 2, that's a 4. So we'll do this calculation. No, that doesn't look right. It's 2047, okay? 2047 because that's the value when we have all the ones being present. Does that make any sense? Because 2047 is 2048 minus 1, which is 2 to the power of 11 minus 1. So now we just have to subtract the quantities of power of 2 of the matching components of the zeros. This 0 means we don't have a 1024, so we subtract 1024 from the all ones. And then this position means we have a 4, so we have to subtract that. And if you look at the calculation of this, does it, okay, this is basically 2047 minus 1028. Does that give us 1019? I think so. Yep, so I think I just double checked my own answer, but without using a calculator. All right, so that means, this bit pattern is expressing the exponent, but with a 1023 bias already applied. Then we group the bits into groups of 4. This is the most significant bit. It will take another 3 bits to become 1 hexadecimal digit. So 0011 is 3. That's the most significant digit in hexadecimal. The next 4 bits will come from these 4 bits. And together they specify F in hexadecimal. The next 4 bits will be these 4 bits here, which will specify a B in hexadecimal. And then the next 4 bits would be these 4 bits here. We're already in the fraction part. This is 0100, which will account for the 0100, which is represented by a 4 in hexadecimal. Are there any questions about how we got to 3FB4 as the most significant 4 digits in hexadecimal? Questions? Then we have 48 bits, okay, of trailing zeros on the right-hand side. But because they're all zeros, I don't really need to specify and count 48 bits or 12 hexadecimal digits. So a left shift by 48 positions will do the same thing. It's just a little shorthand. I don't have to write out all the zeros. Okay. So now the moment of truth is this going to work? And we'll do the same thing as last time. In case you guys forget what I did last time, this is how we do it. So we just write a very simple program, okay? Double EX, I've just called everything the same way. Write a main program. And we also want to do a pound include stdint standard integer.h. So this way we can refer to uint64 underscore t. So this way I guarantee to have this variable as a 64-bit number. If I don't include stdint.h, then I will have to say unsigned long, okay? Because this environment is running in 32-bit, a long is 32-bit, and int is also 32-bit. A long, on the other hand, will be 64-bit. But I don't want to mess with those things because it depends on the architecture, the default width of integers, and so on and so forth. This will make sure that regardless of the architecture, we're dealing with a 64-bit number. So we'll just call this x here. And then we'll just initialize x to the number that we just mentioned. It is 0x, I cannot remember, 3FB4, okay, 3FB4. And we have 48 bits to shift. This is not going to work. Remember last time the compiler complained about this. What did the compiler complain about? You guys don't remember? Okay, let's try that. Okay, if you cannot remember, I'm going to run this through the compiler so that you can see the error from the compiler, and then I'll explain it. Okay, so GCC is fine because it's just a plain C program. -c /ex.c, and well, it's not an error. It is a warning, which means it actually produced code, but the code is not going to do what I think it should be doing. It complains about left shift count is greater than or equal to the width of type. That doesn't make any sense. It is clearly a 64-bit number, and I'm only shifting 48 bits. How can it be out of width? Well, as it turns out, every integer is by default an int. Okay? An int in a 32-bit architecture is 32-bit wide. So that means, if I go back to the source code, I will show you. That means the 0x3fb4, which is a literal integer, is by default just a 32-bit number. What happens when you shift 48 times and apply that to a 32-bit number? You end up with 0. Okay? So that's what the compiler is complaining about is, hey, you have a 32-bit number, it makes no sense to shift it 48 times. I can do it for you, okay, but you just end up with a 0. Are you really sure this is what you want? So the way to fix this problem is to force the constant not to be a 32-bit number. You can, now if you learn this from your C++ class, there are ways to do this. I think UL is one of those. Okay, you can basically attach UL after this. For unsigned long, you can actually do a suffix to a constant to force the type. I'm not going to do this, okay? Since I already have stdint .h included, I can just refer to those things. In other words, I can use the same type of x as x to coerce the constant. So now, 3fb4 has no other interpretations other than 64-bit unsigned integer. Are there any questions? Okay. Do you think this sort of thing can bite you when you're actually working as a developer? All the time, okay? All the time. There are programs who was written for 32-bit architectures. When they bump up to 64-bit architectures, sometimes it doesn't work anymore. Okay, because the assumption of the width being 32-bit is no longer valid. Okay, usually it's the other way around. Okay, usually it's the other way around when you're working normally with a 64-bit architecture, and you are already used to integers being 64-bit wide just by saying int x, and then you suddenly move back into a 32 or even 16-bit platform, then your program doesn't work anymore because the default width of an integer is no longer 64-bit. It is now 32 or 16-bit. So especially with multiplication, division, bit shifting, and stuff like that, those code are very susceptible to the assumption of width of integers. Who would be so insane to move from a 64-bit architecture back to 32 or 16-bit instead of going forward to a 128-bit architecture? Nobody knows. Okay. I'll give you an example, because I do want to bring relevancy to everything that I talk about. Is this a 64-bit processor or a 32-bit? 32-bit, okay. And most of you are running your Windows, okay, especially if you're a new machine, in 64-bit mode, right? So when you write your C++ programs, you will be writing 64-bit code programs, right? Which means a lot of times, if the program works, you just say, oh, okay, my code is correct. And you are correct. Your code is correct with the assumption that the width of integers are 64-bit, okay? So you work out all the math stuff, you work out all the stuff that you can work with using a PC, and then you say, oh, GCC is GCC regardless of the platform, okay? So whatever code that I was able to compile on using Linux as a 64-bit architecture or 64-bit operating system should still cross-compile onto an ARM7 architecture on your phone. Well, the program will compile, but if you turn on the warnings, it will give you warnings like what we just saw because the width of integers have changed. So that means if you ignore those warnings, then your program is not going to work correctly anymore. Okay, especially when you have multiplication involved or division involved, because those things can get out of range the quickest. Addition, subtraction, incrementing, counting, most of those would still be fine because you're unlikely to run out of 32-bit to begin with. So that's why this is actually quite important to specify the width of constants even when you're writing programs. All right, so we'll go ahead and save this program. And then we'll compile this time. It should not complain, so I'm going to turn on -G just so that we can get into the debugger. So GCC dash O double EX dot double EX and then double EX dot O. GDB double EX. Run. Put a breakpoint on line 8. Run the program. Now we can say print what is X. Well, X is a kind of a huge number, which is not surprising, because we did specify a pretty big number. The most significant bits are, a lot of those are ones. Okay, so we want to specify slash t just to see whether we are getting the number that we are supposed to be getting. The two leading zeros are missing because they're not written out, but we have 7 ones followed by a one single zero, 2 ones, and then a 0 1. I think that's what we want. Okay. So the next thing is, let's go ahead and print this one using this trick here. I know there's a different way to do it, but we'll use this trick. Okay. How many people still remember this trick? What it means? What does it do? Okay. Okay. You have to read the code backwards. Okay. Remember in C, a lot of times you have to read stuff backwards. So in this case, we start off with X. Okay. The first thing we do to X is take the address of. Okay. So $x is the address of X, which is the address of a 64-bit integer. And then what do? I do one of the very few things that really make C and C++ a dangerous programming language. I basically say, I know this is an address of an unsigned int, but treat it as an address of a double instead. I'm telling the compiler it's okay to change the type of whatever is at this location. At this point, it becomes the address of a double precision floating point number, right? What do I do next? I dereference. So the result of the dereferencing, the type of what I'm dereferencing, is no longer of that of an integer. It is now of a double precision floating point number. So this is how I can force GDB, and you can use this code in a program as well. You can force your code to look at the raw bit pattern of a location as something else. Okay, which is very useful. Okay, this is really low-level stuff, but it can be very, very useful. So we press the Enter key, and we should see 5 divided by 64. So we'll take a look at that. Well, I'm not a SAE kind of person, so I cannot tell whether that really is 5 divided by 64, and I'm too lazy to pull out my calculator to do this. So instead, what I'll do is to say, let's do this. What should I get? If this is all working out the way it's supposed to, what should I be getting now?
0.
Should be 0, right? Tech, are you really sure that double is needed right before the 5?
Yeah.
What is 5? What is the type of
an
the
integer.
constant 5?
Integer.
It's an integer. So if you have an integer to the left-hand side of division, it becomes an integer division. What is the result of the integer division of 5 divided by 64? 0. Then I'll be getting this number back, and it would seem that my program is not working. So the result is a 0, which is good because this means I actually got it done right. Now you can reverse this too. Okay, this is a reversible process for debugging your next homework assignment, which is going to be converting to / or from, converting a value into or out of a double precision floating point number. What if I give you a floating point number binary representation, and I want the other way around. I want to give you a binary number. I want to give you a value, and you want to look at the actual binary number to check whether your program is doing it right. So we can reverse this process. Okay, how do we reverse this process? We can use set var, right? Set var is one thing we can do. Okay, so we will say set var x equals 2. Okay, but there are 2 ways to do it. The first way is the easy way, because we just use exactly the same code here, but now it's on the left-hand side of the assignment operator, which means whatever I'm storing into is a quote-unquote a double precision floating point number, right?
And it doesn't change the content of it, it just changed how it's read.
Correct.
Okay.
Well, this is changing what we do to the right-hand side. So now on the right-hand side, let's go ahead and specify some other value that is relatively easy to check. Any integer is relatively easy to check. Okay, so we'll start with, I don't know. Today is 1016, okay, so we'll do 1016, okay? So 1016, we want to express it, this is the value we want to represent, okay? So now I can specify 1016. Enough, if I really want to double check and make sure that it will do the base conversion, this is what I'm going to do. So what this is doing is I will force 1016, the value, into a double precision floating point number, and then I'm going to store that as a double precision floating point number into the address of x, which started off as a address of an integer, but I coerce it, I typecast it into the address of a double precision floating point number. Okay, so I can do this, press the enter key, make sure that GDB is not going to choke on this, does not. Okay, but before I really take a look at x, but this time as in binary, as an integer, I want to do this calculation by hand first. So this is the second run or second example of how to do things, but this time it's kind of the reverse of what we did earlier. Okay, well, it's the same process, but I'm checking it backwards. So 1016, I want to express this as a double precision floating point number. So 1016 is 1016 times 1. Okay, everybody knows that, right? But then I'll start to do the conversion now. Because 1016 is, okay, we'll do the conversion real fast here. I already know the answer, but I want to show you the calculation. So what we want to do is we want to convert 1016 into a binary number. How do you convert this into a binary number? Okay, this one is easy because it is really close to this number that we already know, right? What do we get as a difference?
7.
7. And 7 is very easy to deal with because it's just 1, 1, 1 in binary. 1023 is 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. Yeah, 10 ones, okay? Because 2 to the power of 10 is 1024, so 1023 would be 10 ones, okay? We need to subtract 7 from this one. Isn't that an easy one? You don't even need to know binary subtraction to do this, right? So we end up with 1, 1, 1, 1, 1, 1, 1, 0, 0, 0. Okay? So let's go ahead and do this. So this becomes 1, 1, 1, 1, 1, 1, 0, 0, 0, with an implicit point here, times 2 to the power of 0, because that's 1. What do we do next? We want to shift the point to the left until it becomes 1.11111. But by doing so, I have to adjust the power of 2. So I'll do this just by incrementing one place at a time, and then we'll do the quick trick, okay? So we'll do all this, and then say, well, let's move the point to this place. But because I'm shifting the point to the left-hand side, I also have to compensate in the power of 2. Should I change the power of 2 to 1 or negative 1? Do I increase or decrease? I'm already having the value of the mantissa. So how do I compensate for that halving? I have to double, right? I have to double the exponent. So now it is 2 to the power of 1. So you can basically see the number of places we have to shift over. We have to increase the power of 2 by that particular number.
Isn't it more than 1 since you went 3 decimal places over?
Hey, what?
You went 3 decimal places over. Isn't it more than 1?
When I shift this dot from here to here, it went from.
Oh, gotcha.
Oh, okay, I see.
That's what
Some
I was
of the
confused
ones are
about, because
incorrect.
all the
Okay,
ones.
never mind. I get what you're saying. These two are zeros here.
Yeah.
Okay, thank you. Okay, so we just have to count the number of places where we have to shift over. So we have to shift 1, 2, 3, 4, 5, 6, 7, 8, 9 places. So that means this 0 will become a 9 here. Okay. So without going through all the individual steps, we can now say it's 1.11111000 times 2 to the power of 9. Are we still doing okay so far with this? Now, it is implicit that this part here, the mantissa, is in binary, but the rest is still in base 10. Okay, so I just want to make it clear that only a part of this number is in base 2. Okay, so now I can actually write down what we need to represent in binary, because what we need to represent in binary would be, let's make this more fun. Let's make this a negative value. Okay, so we want to represent a negative value. So the sign is going to be a 1. The exponent, and this time I will integrate the bias into it right away. The bias is 1023, which means if I want to represent 9, we have to add 9 to the bias. So it becomes 1032, okay? And we also want the mantissa to be 1.111111 and then all zeros. But since we only use the fraction part, only that part is explicitly represented. That means we only want to take this part and represent it in the actual binary bit pattern. So it becomes 11111, 6 ones, and then a whole bunch of zeros. Dot, 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 like that. Okay, so the only thing left to do is to convert 1023 into a binary bit pattern. This is also an easy one because it's 1024 plus 8. Okay, that makes it a very easy one. So we have 1 for bit 10. Okay, this is the most significant bit. And then we have another 1 for the bit position corresponding to 8, which is 3 positions from the right-hand side. So we have 1, and then we have to specify a bunch of zeros. Let's see how many we have to specify here. The whole thing is 11 bits. So we have to specify 6 here. 1, 2, 3, 4, 5, 6. So now we have 7 digits, and then we have 4 digits left, which is just enough for my 8. So I think that is 1023. Let's double check. Okay. 1, 2, 4, 8. Okay, that accounts for the 8. Now we have 1024 left. 16, 32, 64, 128, 256, 512, 1024. So I think that's correct. I know most of you do not think that you need to do these calculations by hand or mentally, but trust me, it does help when you are familiar with binary numbers. So if you have a chance to do it, just not using your calculator, do it on a piece of paper or do it mentally, it really, really helps. Okay, it helps down the line. Okay, so now we have everything in binary, and we just have to group all of these bits into groups of 4, because we want to look at this number as a hexadecimal number. So this 1 accounts for the most significant bit. This is a 1. We pick out these 3 bits from the exponent as the next 3 bits. So we have 1, 1, 0, 0. The next 4 bits are these 4, all zeros. And then the next 4 bits are these 4 bits, 1, 0, 0, 0. And then the next 4 bits will be in the fraction part, all 1s. And then the next 4 bits will be these 4. And then we just have a whole bunch of zeros after that. So when you look at this as a hexadecimal number, this is a C. Oops. This is a 0. This is an 8, F, C, and a whole bunch of zeros. Which also means I can look at this as in hexadecimal, C08FC, and this time we have to shift it by 44 positions and not 48, because we have already accounted for 20 positions in bits already. So we only have to shift into 44 zeros to make up for 64 bits. Are there any questions about this process? Yep.
Can you explain the 44 again?
64?
The 44.
The 44?
Yeah.
Because C084C specify 5 hexadecimal digits. Each hexadecimal digit accounts for 4 bit positions. So together they will account for 20 bit positions already, the most significant 20 bits. And because we're dealing with a 64-bit number, the least significant 44 bits in this case would all be zeros. So instead of specifying 11 zeros, I just use the left shift operator, so to save some typing, basically. All right, so now that we know this is the number that we're dealing with, we'll go ahead and, since I really cannot remember the digits, I'm going to do this. Go back to my GDB session. And this time we'll take a look at the actual representation. So we'll say print /x in hexadecimal. What is in variable x itself? So I stored the value as a double, but I now print it out as an integer in hexadecimal. So we'll try to see if it does match what we are expecting. That's not, oh, because we forgot the negative. Sorry about that. Now we can do it. Okay, question is, does this match what we had earlier? I think it did. There we go. Yep. So GDB combined with a very simple program written in C is a really good tool to help you understand how double precision floating point numbers are represented. And for your next homework assignment, this is one thing you can do, just quickly verify, are my steps making any sense? Because you can check along the way of every step. I'm not going to assign that homework assignment just yet, but you want to think about it, okay? Just think about what you need to do in order to represent a value that is in decimal, okay, into a double precision floating point number. And I can kind of tell you what is the input. The input is going to be in decimal. So I'll give you a decimal number using the exponent, the e to the power of e means times 10 to the power of some power. So everything is going to be in base 10. So you have to take that representation and turn it into the double precision floating point number representation, but without using any C++ function to do it. Because that would be way too easy. There's a function called ATOF that does exactly that. ATOF stands for ASCII to float, which is doing what your homework assignment is supposed to do. But I want you to go through this manually, write your own code eventually to do this. It's not assigned yet, but it's time to start thinking about it, because it is not an easy one. It's kind of tedious in many ways. But that's how numbers are represented, as a double precision floating point number. Are there any questions regarding the representation of floating point numbers? No questions? How do you guys want to write the code to do addition with floating point numbers? Is that going to be an easy thing to do, since we already covered all the adders and stuff like that already? It's not easy, okay? Because if the exponents do not align, then you have to shift one of the numbers so the implicit binary point is lined up before you can actually carry out the addition. Okay? Multiplication turns out to be the easier one, because you just multiply the mantissa, you add the exponent, and there's a potential that the mantissa will have a product that is no longer 1 point something. It potentially can go up to like 1 point something. Well, we can take care of that. That's one shift. Okay? So multiplication turns out to be a lot easier compared to addition when you're dealing with floating point numbers. We are not actually going to do that. I'm just making you guys think a little bit and say, okay, if I have to deal with addition in floating point numbers, what do I have to deal with? Any questions? No questions? Okay, so if there are no questions, I'm going to stop the recorder, because that's all there is today to the week. Uh-oh, where's my recorder? Oh, right there.